Good evening. My name is Kabagay Salim and I'm here on part of Group 9. Me and my fellow group mate, Kashar Alvin Salih, shall be taking you through generative attention-based mechanisms for fake currency no detection. I'll begin by asking a question. This is what we shall be talking about. Of course, me, I'll talk about the first four topics, and then my group mate also talk about the preceding ones. So I'll begin by introducing the background introduction of our study. If I'm to ask a question, we all know that fake currency has led to losses of billions and billions of money each year. So who doesn't know that? Then, if I'm to define fake currency is just this money that is illegally printed by other companies or other individuals or other businesses even to resemble the real money that is printed by the government. So why is this a concern? It is a concern because fake currency has led to losses in businesses whereby some people are given fake currency in form of trade. Let's say I'm selling you a commodity, and then in return to pay for the commodity, you give me a fake note. Of course, that one hinders my business in form of losses. And then another thing, it reduces the trust of the public to the government, whereby if a lot of money is a lot of fake money is in circulation, it means that most people won't be believing in the government that is in power. And this is because in the long run, these counterfeit currencies lead to inflation. How? Because they reduce the value of the real money. And then, if I'm also talk about the background, fake currency started way back a long time ago, during the gold and diamond ages, whereby most people would put metals of low quality and mix them with gold and diamond, and then for them to act as counterfeit because those ones were not legally accepted by that time. And then also in world wars like World War II, um, the the enemies, let's say one country is fighting with the other, let's say Russia is fighting with America, the enemy, and Russia would get counterfeit money and fund the allies of America. And that was also hindering the progress of the war in the long run. And then, how is fake currency made today? Fake currency is made today through digital printing, whereby a lot of security measures are put up. For example, watermarks, um, serial numbers, which are hard to be faked by these other companies. But of course, with the coming of great technologies and AIs, these monies are being forged by those companies, though we have all those security features. So it's on this note that I bring you the impact of this. Like I'd said before, yeah, it leads to losses in businesses, uh, lack of trust by the public to the government, and also these fake currencies are also used by the criminals. Let's say terrorists are also used by the terrorists to fund their programs. For example, buy firearms and stuff. So, if I'm to discuss about the related works, recent trends and literature review, um, the existing counterfeit detection methods, of course, we know we have manual inspection. That was a long time ago, but even for small businesses, they still use manual inspection, whereby they get the money and just look at it and say, okay, this is fake or real. And also others use this light scanning. They put the note in light and then see the watermark. And then we have UV and infrared scanning for medium business, let's say circles and small banks. They have UV lights detectors to detect if a currency, if a note is real or fake. We also have the traditional CNNs and service vector machines. These ones are also kind of improved, but of course they struggle with fine-grained security features. These ones which are hard to implement, like watermarks. Then advancements that are now taking place, of course, we are having vision transformers. The vision transformers, they divide a picture, let's say an image, into patches, and each patch is analyzed by the model to detect to detect those security features like watermarks and other features in form of feature extraction. And then we are having CNNs. Of course, these ones use a lot of convolutional layers to 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 get those features that are on the node. For example, watermarks, serial numbers, um, and others. Then also have graph attention networks. These ones use an attention function, and this attention function, what it does, just gives focus to those special features. It's some sort of priority. It uses priority checking and gives priority to those features that are relevant to what you are working on. Let's say, for example, if it's in current detection first, it gives attention to those features, for example, watermarks. Then also have generative adversarial networks. These ones are mainly focus it's a two model architecture. It has the discriminator and the generator. The discriminator, it has to say if this image has been generated by the generator, then it's either real or fake. Then the problem statement, there are various problems that are brought up by the fake currencies. For example, we have the economic impact, like I'd said, it brings up inflation in the long run because this fake money will be more than the real currency in circulation, and of course, in turn, it will lead to inflation. Then another point, it's about business losses. Of course, someone comes, buys a product, and in exchange, he gives you a fake note. That's a loss to the business. And then another point, it's athlete to the financial sector, because the government will try to make sure it facilitates all those companies which can help it cap down the fake currencies that are in circulation. And in turn, you find the government is spending a lot on these things, which is a loss financial to the government. Then, of course, there's also crime funding by terrorists. These fake currencies are used by terrorists to fund their programs, for example, buy firearms and stuff. Then it also leads to public distrust. People lose trust in their government, which is something that is bad for the government in power, because in the end, it will be out. Then, how can we cap down all we can cap down all these because there are very many things that are being brought up. For example, the advanced AIs, which can be used together with the models I've been saying, the VITs, the GANs, the GATs, to make sure these currencies are reduced, the fake currencies are reduced. Then also, we have to also do public awareness, whereby you have to get those programs and educate the public about fake currencies and how to avoid them and how to detect them. Then on the research questions and objectives, this is where my group mate, Kasha Alvin, will begin from to give us more insight about it. Thank you.
Starting off with the methodology, I would simply start off with an input backnote image that maybe would be scanned, and then we'll come up with a soft copy that is actually entered. And then we have image processing as the first step in the system, where we actually have the image resized and also deal with noise. And then we could also think of feature extraction using vision transformers to capture the actual features and patterns in the image. And then to assign weights using graph attention networks and come up with the most important features through visualizations and next modes for the image. And they just because fake samples of the currency notes are scarce in real world scenarios, we could use GANs generative adversarial networks to generate fake currency samples, and then also have knowledge distillation, where we would have the teacher model, let me say a GAN of VIT training, having or developing model, rather developing data, or developing data that would be used by the student model, let me say like a CNN, to do its own prediction. And then we'll come up at the end up with a classification of real fake based on the image input. Next, the data set description. The data set we obtained contained both fake and real currency notes, and they were in the domination of the 500 Indian rupee and then the 2000 Indian rupee. And then On that, after that, we have the output. After the model evaluation, we came up with, we're able to ascertain that we're going to deploy an ensemble learning technique known as the random forest test because it portrayed anonymous significant values after the evaluation scores were awarded. We go to come up with a matrix, confusion matrix, as you could see. So it correctly classified 6 instances of real images as real, and then fake instances of fake images to be fake. And then it had two misclarifications why it actually misclarified real not to be fake and then fake not to be real. Then we trained other models. I could think of this, the CNN, the mobile net to test the efficient net beef and so on. And this was actually the training and validation accuracy. As you could see, we in the training, we had a quite small number of epochs. We trained the models, of course, implementing early stopping, such that if the learning rate would be intimate, if you'd stop at one point in time, the model would actually drop up early enough in the number of epochs without reaching the maximum. So the orange line represents the validation accuracy, and then the blue line represents the training accuracy. The y-axis represents the accuracy, and then the x-axis represents the number of epochs. So you could immediately see that as the model was starting, it started off with an increasing accuracy in terms of validation, and then it massively dropped towards as the numbers of epochs were increasing, and then it also increased the validation accuracy, kept on increasing the validation accuracy up to 0.65, then dropped as so on and so on. And then the very same happened for the training accuracy. It increased, a sharp increase from the first epochs, and had 0.565 accuracy, that would be 65%. And then it kept on weighing up and then also decreasing with time. Then where there is accuracy, there's also loss. So those are the training loss and validation loss for the CNN model, where you could actually see that I started off with a decrease, and over 2 epochs, you could see on the x-axis, and see that already these are number of epochs, and then this is the loss attached on the y-axis, and then the training loss is the blue line, the validation loss is the orange line. Then, of course, the other evaluation scores based on accuracy, precision, recall, F1 score, these were awarded to the random forest that could easily sit at an accuracy that was above 75%, and then a precision that topped up to 100%, and then, of course, not leaving behind the recall function of remembering where it would actually see in the images before. And then it had an immense F1 score of 78%. And then after that, we had an image data set that had current 2000 bank rupee notes, and then we were able to establish histograms to showcase the blue channels and green channels distribution in the pixel intensity of the images. So you could see they were highly cumulating up to 0.35, having the green channel at 0.25, the maximum, and then the red channel being at 0.4. Then we also had the training and validation loss for the mobile net. Mobile net is a model that was portrayed for the edge devices, e.g. mobile phones, but you could easily see that it had training loss that was incrementing, decrementing over various number of epochs. You could actually see from, it dropped from 2 and it went to 1.9 over the epochs of 2. And then since we're training models, we actually managed to evaluate some of the learning rate based on a learning rate schedule function we had made over a number of epochs. And this would actually show that the learning rate started off as constant over 25 epochs and then dropped immensely over the approximately 30 epochs, and then kept on decreasing until it maintained a constant state rate, learning rate towards the 200 epochs. And then this was the overall evaluation score basing on model accuracy and precision and F1 score. These are the various models we deployed, as you could easily visualize. And these were the scores we awarded. As I had said, we deployed the random forest just because it had the most accuracy in classifying image data as fake and real currency notes. And then next in line was a support vector machine that had 79.2%, and so on and so forth. And then the conclusion, of course, we developed a number of machine learning models as I had previewed earlier, but then we were able to deploy the random forest just because it had a good accuracy, testing accuracy. The key accomplishments are improved accuracy, as the model could actually classify fake and real currency notes. And then we also managed to implement a vanilla GAN that I integrated with some FCGM to produce fake synthetic data just to solve the problem of a scarce data set in terms of fake notes. Then limitations, we had limited data sets, since, as I earlier said, it's hard getting fake notes, limited resources in terms of processing power of computers. Some of these models needed high processing power and could not achieve this on local machines. Data imbalance just because of the little data on the fake samples, and if the data set was enriched with real samples, real currency notes, then the data quality in terms of the images that were generated by the GANs. And then the feature works we think about enhancing graph construction using graph rotation networks, and then also increasing the availability of fake data samples just as to enrich the data and maintain data balance. And then also you could think of implementing lightweight models through knowledge distillation just as to work on edge devices such as mobile phones.